All right, welcome to lesson 7.4 on solving radical equations. I'm going to split this video into two parts. This first video is just going to tackle the basic premise of what we need to do in order to solve radical equations. The second part video, part 2, will cover a little bit more complicated problems and some more advanced techniques of doing that. Or maybe just sort of combining our previous learning from past units into this unit. Because quadratics and quadratic patterns and factoring do make a return in specific instances. Not for all of these problems, but there are a few problems where we're going to have factoring come back at us. But that's part 2. So part 1, I'm just going to focus on the idea of how do you solve a radical equation? What's the goal? What are we trying to do? So let me get my little gold here. Where's my gold? Okay. So I'm going to read some basic things you probably already know before watching this video, and that is the inverse operation of raising to the power of 2, right, taking an exponent of 2, is taking the square root. We already know that, though, don't we? Right? If I have... let's say, right, if I have 5 squared, right, then if I take the square root of 5 squared, this becomes 5, right? Because the square root of 25 is 5. And so you can, if you apply the square root to it, it goes away, essentially, right? Okay, you might say, well, why does this actually work, right? And you can look at the basic premise of the relationship between squares and their square roots. But if we were maybe looking just algebraically, why does this work? Well, we defined the square root of x to be x to the power of 1/2. So let's say I take x squared, right? And I'm taking the square root of that. The square root of x squared. Well, the square root of x squared, if square root of x is written as x to the power of 1, the square root of x squared could be written as x squared to the power of 1/2. And if you recall your exponent rules, when I have a base with an exponent raised to another power, to kind of compute that, I can multiply the powers. So I get x to the power of 2 times 1/2. Of course, 2 times 1/2 is 1. So I have an x to the power of 1 here. Now, I don't really need to write that little 1 right there, but that is the idea, right? And so that's kind of why it works, right? If you just wanted to look at it from a different perspective. Right, if I define square root of x to be x to the power of 1/2, then by using this definition, I can find that by raising to the power of 1/2, those exponents cancel each other. You can also see this as if I had x to the power of 1/2, you can raise this to the power of 2 for the same exact reason, 1/2 times 2. So it works for both, right? That's why they are inverses of each other. Let's take a look at cubes, right? The inverse operation of raising to the power of 3 is taking the cube root. So you can see this as, right, if I say the cube root of, sorry, I meant to write x cubed. X cubed, if I wanted to isolate x, then I could take the cube root of x cubed, and that would give me x. So similarly, I'm going to make kind of the same exact thing as what's above. If we define the cube root of x to be x to the 1/3, then it follows that if I take x cubed and then I cube root it, you can rewrite this with a rational, you can rewrite this as rational exponents. So it's x to the power of 3 to the power of 1/3. And of course, just like the above example, that's 3 times 1/3, yielding x. So you can see that when you raise it to this power, you get x. You get x alone. You get the radicand all by itself with no more radical sign. Okay? So we can generalize this for any rational exponent. That rational exponent being the power of m over n. So what I've written here is the inverse operation of raising to the power of m over n is to raise to the power of the reciprocal, which is n over m. So to see how this might work, right, if the nth root of a to the m, I have this, well, I can rewrite this, I'm going to rewrite this as a to the power of m over n. Now, if I raise this, so I take a to the m over n, and I raise this to the power of n over m, well, same idea of those exponent properties. This is m over n times n over m. Those cancel, and I am left with the radicand a. It sort of undoes it, right? You can kind of think of this as similarly. What I'm doing here is two operations in one. I am taking the nth root of a to the m, and first, well, it actually doesn't really matter what order you do it in, but I might say it's like taking the nth root of a to the m and raising it to the power of n, so that it's a to the m, and then it's taking the mth root of a to the m, which equals a. So you see it's doing two things. It's raising to the power of n, and it's taking the mth root, which is the power n over m, right? Because the numerator means raise it to the power of n. The denominator means take the mth root. And so that's kind of why that works. And so I might write this in red here. I might jot this down in your notes to isolate the radicand, assuming you want to do that, right? Raise to the reciprocal power. I might write that down. So if you want to isolate your radicand, because that's usually where our variables are going to be, is under that square root, just raise it to the reciprocal power. And that's it. That's pretty much all you need to know. I made this little face here. See. Okay, so let me go through a couple examples so you might see this in action, about how we might use these reciprocal powers. Example 1 is really quite straightforward. You could probably solve this without me or even without seeing this video. But I'm going to write it using rational exponents to kind of see how that comes into play and why that works. So let's take example 1. Let's solve this equation that's given to us in radical form. The first thing I want to do is isolate the radical. So I'll subtract 5 from both sides, getting me negative cube root of 4x plus 7 equals 2 minus 5 is negative 3. I will then divide both sides by negative 1 because I want to, I really just want to get that radical alone and make it positive. I will say this, you don't have to divide by negative 1. You could actually go ahead and cube both sides. However, I like to just get rid of the negative because you have to be careful if you're going to do that. And maybe we can talk about that in class as to why. But anyway, from here, you should see that you can cube both sides. And if you do that, right, you get, cube root of 4x plus 7 cubed equals 3 cubed, which this is when you cube root that, or sorry, when you cube the cube root, you get 4x plus 7 equals 3 cubed, which is 9. I'm sorry. Why did I write 3 squared? 3 cubed, silly. It's supposed to be 3 cubed, Mr. Spake. So it's not 9, it's 27. From here, that's a very basic equation we can solve. Subtract 7 from both sides. I get 4x equals 20. Divide both sides by 4. Therefore, x equals 20 over 4, which is 5. And that's not a kind of rectangle I wanted. If you've watched my videos before, you know that I like those pretty rectangles. Okay. So there it is. And you probably didn't need this video to know how to do that, right? I mean, you've probably done stuff like that before. But I wanted to give the example so you understood kind of what's going on. You could also think of this, I'm going to say alternative in yellow, is to rewrite this as 4x plus 7 to the 1/3, right? Because cube root of 4x plus 7 is 4x plus 7 to the 1/3 equals 3. Then if you cube both sides, right, if I say, oh, well, take 4x plus 7 to the 1/3 and raise it to the power of 3, and then take 3 to the power of 3, then this implies that it's 4x plus 7 times 3 times 1/3, which is just 4x plus 7. And then that equals the 3 cubed, which is your 27. And then, of course, it is the same exact process, minus 7 from both sides. You get 4x equals 20 again, divided by 4, leading to that same exact result, x equals 5. Okay, you don't have to write it that way. I just wanted to show you that if you rewrote it with rational exponents, you can use the reciprocal of 1/3, right? It was to the 1/3 power. I then raised that to the 3rd power. That's the reciprocal of 1/3. Okay, let's look at one more, example 2, and then I'll end this video. And I hope this isn't going too long. I hope I can wrap this up soon. Okay, so let's solve an equation using reciprocal power. Same idea. Again, I want to isolate the radical, meaning I want to isolate, you see, x to the 3/2. Well, that's square root x cubed, right? That's what that is. So that's my radical term. So that's what I want to isolate. So let's start by multiplying both sides by 3. Multiply by 3, multiply by 3. Then I get x to the 3/2 minus 4 equals 20 times 3 is 60. Then I can add 4 to both sides. So this gets me x to the 3/2 equals 64. So let's take this, right? Let's take this result. X to the 3/2 equals 64. The way I isolate x, the way I get rid of this power, is by raising to the reciprocal. And the reciprocal of 3/2 is 2/3. So over here, it's 2/3. So the left side, you see, becomes x to the 3/2 times 2/3, which is just x. But the right side equals 64 to the 2/3. Now the question is, what is this? Because you don't want to leave this. You want to simplify this 64 to the 2/3 business, right? So I can rewrite this. Let's say x equals 64 to the 2/3, which equals the cube root of 64. And where we put that exponent of 2 is up to you. If you would like to square 64, you can. Or what I like to do is it's easier to take the root first and then square that result. Remember, we're allowed to do this because of the rule, which says, I'll write it in yellow. Remember, rule, a to the m over n equals the nth root of a to the m, and it is the nth root of a to the m. So what I'm using here is this rule, right? This and this. That's the rule I'm using. Okay, anyway, I just wanted to highlight that so it's very clear. You can take the cube root of 64 because 4 cubed equals 64. Therefore, the cube root of 64 is 4. And so this is equal to 4 squared, which is then equal to 16. So hence, I'll say therefore, x equals 16. And done. So there it is. There's a nice example of solving with reciprocal powers. Notice, again, to recap, all I did was I isolated that x term, and then once I did that, I raised to the reciprocal power, meaning whatever fraction it is, flip it and put that as the power instead. And yeah, that's the basic premise. That's all you really need to know going into class. But I do recommend continuing on to part 2 and seeing the more complicated examples because they can get tricky. All right, they can get really tricky. And you might get stuck, especially when what we're going to cover in the next video is what happens if I have something like this. Ooh, or maybe I like it that. Ooh, what do I do, right? And that's what we're going to talk about in that video. So hopefully I'll see you there, and have a good rest of your day.